This talk is about adjacency labeling schemes for planar graphs and is joint work with Vida Dujmovic, Louis Esperet, Cyril Gavoille, Gwenakl Joret, and Piotr Micek. Let A be a function that takes pairs of binary strings as inputs and outputs a single bit. Now, take a graph G and label its vertices with binary strings. We say that this labeling of G works with A if the following conditions are satisfied. When given the labels of any two adjacent vertices in G, A outputs 1. When given the labels of any two non-adjacent vertices in G, A outputs 0. We refer to A as an adjacency tester. We say that a graph family has an f of n bit labeling scheme if there exists a single adjacency tester A, such that each n-vertex member of the family has a labeling using labels of length f of n that works with A. The example shown here uses an adjacency tester A that returns 1 if and only if the Hamming distance between its two inputs is 1. The graph illustrated here is a 3-cube. The labeling is the standard labeling of the 3-cube using labels of length 3. This generalizes to the d-cube and shows that the family of hypercubes has a log n bit labeling scheme. Adjacency labeling schemes are closely related to so-called universal graphs. If a graph family has an f of n bit labeling scheme, then for each integer n, there is a universal graph un with 2 to the f of n vertices, such that each n-vertex member of the family appears as an induced subgraph of un. The graph un is easy to define. Its vertex set consists of all f of n bit binary strings, and an edge vw is present in un if and only if the adjacency tester A outputs 1 given the binary strings v and w. Nearly optimal adjacency labeling schemes and universal graphs for trees and forests have been known since the work of Chung on universal graphs in 1990. Work in this area has recently culminated in the result of Alstrup, Dalgaard, and Knudsen, who give a log n plus O of 1 bit labeling scheme for the family of forests. This is optimal up to the constant additive term. As part of their work on planar graphs, Gavoille and Libre showed that the class of bounded tree width graphs have near optimal labeling schemes. Work on adjacency labeling schemes for planar graphs goes back at least to 1988. Muller's thesis describes a 6 log n bit labeling scheme based on the fact that planar graphs are 5 degenerate. In a stock 1988 paper, Kanan, Naor, and Rudich describe a 4 log n bit labeling scheme based on the fact that the edges of a planar graph can be oriented so that the maximum out degree of any vertex is 3. The fact that the edges of any planar graph can be partitioned into 3 forests, along with the optimal labeling scheme for forests, implies a 3 log n plus O of 1 bit labeling scheme for planar graphs. Gavoille and Libre use the fact that the edges of any planar graph can be partitioned into 2 graphs of tree width 2, along with their labeling scheme for bounded tree width graphs, to obtain a 2 log n plus little o of log n bit labeling scheme for planar graphs. Very recently, Bonamy, Gavoille, and Pilipchuk used a recent product structure theorem for planar graphs to obtain a 4/3 log n bit labeling scheme for planar graphs. Finally, the main result in the current work is a log n plus little o of log n bit labeling scheme for planar graphs. This work is also based on the product structure theorem, and is optimal up to the lower order term. Before we can describe the product structure theorem on which these results are based, we need to define the strong graph product. This figure illustrates the strong graph product of a tree and a path. The product of two graphs A and B is the graph whose vertex set is the Cartesian product of the vertex sets of A and B. A vertex A1, B1 is adjacent to a vertex A2, B2 if one of the following 3 conditions are satisfied. A1 equals A2, and B1 and B2 are adjacent in B. These are vertical edges in the illustration that join 2 vertices in the same column. A1 and A2 are adjacent in A, and B1 equals B2. These are horizontal edges in the illustration that join 2 vertices in the same row. A1 and A2 are adjacent in A, and B1 and B2 are adjacent in B. These are the blue and red diagonal edges in the illustration that join vertices between distinct rows and columns. As in the example shown here, we will always be taking the strong product of some graph and a path. In this kind of product, the vertical and diagonal edges always span 2 consecutive rows. The product structure theorem for planar graphs states that any planar graph G is the subgraph of a strong product of 2 very simple graphs, a bounded tree width graph H and a path P. Our main result is that any family of graphs consisting of subgraphs of strong products of bounded tree width graphs and paths has a log n plus little o of log n bit labeling scheme. This result applies to graph families considerably beyond planar graphs, including bounded genus graphs, apex minor free graphs, bounded degree graphs from minor closed families, and k-planar graphs for constant k. Before proving the main result in its entirety, we consider the special case in which G is an induced subgraph of the strong product of two paths. This simpler sounding problem still contains all the major difficulties that must be overcome in a solution to the general problem. The vertices of G can be partitioned into rows numbered 1 through h. We let Gi denote the subgraph of G induced by the vertices in row I. Each vertex label has three parts: a row label, a column label, and a transition label. The row label identifies which row I, V is in. Every vertex in the same row receives the same row label. The row labels are designed so that using the row labels of two vertices, we can determine if the vertices are in the same row, in two consecutive rows, or in two distinct rows that are not consecutive. If row I contains ni vertices of G, then the label for row I will have length roughly log n minus log of ni. The column label of V is designed so that given the column labels of two vertices in the same row, we can test if U and V are adjacent in G. The column labels are designed so that each vertex in row I receives a column label of length roughly log ni. In this way, the total length of the row and column label for V is roughly log n. The discussion so far already highlights the main difficulty. The row labels of two vertices V and W have three cases. If V and W are in the same row, then we can use their column labels to test if VW is an edge of G. If V and W are not in consecutive rows, then we know that they're not adjacent. But if V and W are in consecutive rows, I and I plus 1, then we have a problem. The column label for V is in the graph induced by row I, and the column label for W is for the graph induced by row I plus 1. These are different graphs, so the column labels of V and W are not compatible. For this reason, the label of V contains a third part, called the transition label, which contains enough information to modify the column label of V to produce a column label that's compatible with the labeling of row I plus 1. Then we use this modified label to test for the existence of the edge VW. To implement these ideas, we need a flexible way to label the vertices of a path. One way to label the vertices of a path is to store these vertices in a binary search tree T, in the same order they occur on the path. Each vertex V gets a unique signature obtained by recording the steps from the root of the tree to V using a 0 for an edge leading left and a 1 for an edge leading right. In addition to this signature, each vertex implicitly stores the signature of the vertex that immediately precedes it in the path. The key observation here is that this signature has a concise encoding. There are three cases that can be distinguished using two bits that are denoted by an O, an A, or an X in the illustration here. In case O, the predecessor V in the path is not part of the induced graph. In this case, there is nothing more to encode. In case X, V has no left child. Then the signature of V's predecessor is obtained by removing a trailing string from V's signature that consists of a 1 followed by a string of 0 or more zeros. This does not require encoding any extra information. Finally, in case A, V has a left child. Then the signature of V's predecessor is obtained by appending a 0 and a string of 0 or more 1s to V's signature. This can be encoded by a binary encoding of the difference in depth between V and its successor. The code for V, therefore, consists of a signature, whose length is equal to the depth of V, 2 bits to distinguish between case O, X, or A, and possibly a positive integer that is not greater than the height of T. If T is at all balanced, this final integer can be encoded using O of log n bits. It's important to note that the parts of the label other than the signature only contribute O of log n to the length of the label, so our discussion will mostly focus on ensuring that the signature of any node is short. We will create a sequence of binary search trees T1 through TH corresponding to the rows of our graph. We want two consecutive trees in this sequence to be closely related, so the first step is to apply fractional cascading, a technique from data structures, so that any two consecutive rows are not wildly different. This does not increase the total number of vertices by more than a constant factor, but ensures that there is no long sequence of vertices that appear consecutively in row I, none of which appear in row I plus 1, or vice versa. Before describing this tree sequence, we first dispense with the problem of finding row codes. Since there are no restrictions on the binary search tree T used to create these codes, we can use a biased binary search tree. For each integer I in 1 through h, we assign a weight equal to the size of the tree Ti. If we build a biased binary search tree using these weights, then the node that contains the value I will have depth log n minus log of Ti plus a constant. This means that the label for I will have length log n minus log of Ti plus O of log n, as required. All that remains to show is that we can assign column labels to nodes, so that each row in node I receives a label of length at most log Ti plus little o of log n. Coming back now to the column labels, we'll imagine the tree sequence T1 through Th as a single dynamic binary search tree that undergoes changes as we move from one row to the next. We call this structure a bulk tree, since the operation of moving from row I to row I plus 1 involves many additions and removals. When moving from row I to row I plus 1, three things happen, and we need to keep track of how this changes the signatures of nodes that appear both in Ti and in Ti plus 1. These changes determine the transition codes that are used to convert the signatures of a node in Ti into a signature that can be used in Ti plus 1. These three changes are the addition of new nodes that appear in row I plus 1, the deletion of nodes that disappear from row I, and a rebalancing operation required to ensure that each tree Ti has height that is very close to the logarithm of its size. The addition of new nodes that appear in row I plus 1 is done using a simple algorithm. Each new node from row I plus 1 has an external node in Ti that it could replace. The fractional cascading step ensures that for any such external node, only a constant number of new nodes could replace it. These new nodes are then grouped into a perfectly balanced binary search tree whose root replaces the external node. This does not increase the height of the tree by more than a constant. This addition has no effect on the signatures of nodes in Ti that also appear in Ti plus 1. Any node that appears in both trees has the same signature before and after the new vertices are added. The deletion of nodes that disappear in row I plus 1 is done using the standard algorithm for deletion in binary search trees. If the node is a leaf, then we simply delete that leaf. Otherwise, we replace the node with either its successor or its predecessor, as illustrated here. This can cause a sequence of nodes to change locations, where each node in the sequence takes the empty place left by its predecessor in the sequence. The key observation here is that any node that moves replaces one of its ancestors. The only effect this has on the signature of the node is to truncate it. Any node that is not moved by the deletion has the same signature before and after the deletion. Therefore, for a particular node V that appears in Ti and Ti plus 1, the effects of any number of deletions on the signature of V can be summarized by a single integer that indicates how many bits to remove from the signature of V. If Ti is at all balanced, this integer can be encoded using O of log n bits. Note that deletions do not increase the depth of any node, and therefore they do not increase the height of the tree. Furthermore, fractional cascading ensures that the size of Ti and Ti plus 1 do not differ by more than a constant factor. Therefore, the logarithms of their sizes do not differ by more than a constant. So far, we've seen that the changes to any node signature when performing all the insertions deletions required to move from Ti to Ti plus 1 can be encoded using O of log n bits. Furthermore, if Ti has close to optimal height, then Ti plus 1 nearly does as well, except for a constant increase. Over many rows, these constants add up, so some kind of rebalancing has to be done. For this, we do a very rough rebalancing operation that works on a node x. At the end of this operation, every node of depth k in the subtree of x contains at most 1 over 2 to the k nodes in the subtree of x. Clearly, this operation only affects the signatures of nodes in the subtree of x. By implementing this carefully, the changes to these signatures can be encoded in O of k log n bits. When moving from row 1 to row 2, this rebalancing operation is applied at the root of t. When moving from row 2 to row 3, it is applied simultaneously at all nodes of depth k. When moving from row 3 to row 4, the operation is applied to all nodes of depth 2k, and so on. This continues for some number y of iterations until y times k is greater than the height of the tree. At this point, the process repeats, beginning from the root. The analysis is intricate, but the main idea is that this operation operates on k layers of the tree at once, but the insertions and deletions performed only increase the height of the tree by a constant. By choosing k large enough, this ensures that the height of the tree never exceeds its optimal height by more than a factor of 1 plus 1 over k. This leads to a trade-off in which the transition codes have length k log n, and the height of the tree t exceeds its optimal height by at most log n over k. Optimizing the value of k gives a total label length of log n plus O of square root log n log log n. Of course, there are many details missing from this short talk. One of these is how the solution for the strong product of two paths can be extended to the strong product of a bounded tree width graph and a path. Very roughly speaking, this is done by embedding h, a bounded tree width graph, into an interval graph of logarithmic thickness, and then using a tree t that corresponds to an interval tree for the resulting set of intervals. A final detail is that these labeling schemes have to work for all subgraphs of h times p, not just induced subgraphs. This is handled in a fairly straightforward way by using an orientation of h times p in which each vertex has outdegree at most d. Then the label of each vertex includes a bit vector of length d that indicates which of its outgoing edges in the induced graph are actually present in the subgraph. This concludes our brief overview of the area and the new result. An obvious open problem left by this work is to determine the second order term. The current upper bound is O of square root log n log log n, while the only known lower bound is omega 1. Thank you for listening.